slide. All right, so the general idea of equilibrium is that at some point during a reaction, the rates of the reactants turning into products and then the products turning back in the opposite direction into reactants are going to be the same. We kind of summarized in the last 7 months and just talked about reactions going in one direction, when really reactions are going in two directions. So you have your reactants turning into products, and that's all we really said. But in the same time, what happens is actually some of the products go in the reverse direction and can turn back into reactants. So like an everyday example might be like you building something out of Legos, and every time you're putting something together with your Legos, somebody else is taking those apart and breaking it apart. At some point during that experience, you're going to be doing it at the same rate. So for every 2 Legos that you put together, your little sister is taking apart those 2 Legos. So you're kind of equalizing. So that's the idea of equilibrium. So we say that equilibrium is the state where the forward reaction, which is what we almost always talk about, reaction would be RxN, and reverse reaction are occurring at equal rates. Oops, let's see. There we go. Okay, so this usually we call dynamic equilibrium, because dynamic implies that things are still moving, things are still happening, okay? And so dynamic equilibrium means that things are still happening. You're still having this forward reaction, and you're still having the reverse reaction, that they're both occurring. But on the outside, it doesn't look like anything is happening, okay? So that's the idea, that macroscopically, there's no overall change. If somebody just walked into the room, they'd see that you had 4 Lego pieces put together. And then 10 minutes later, you might have 4 Lego pieces put together. But your little sister is taking them apart as fast as you can build them. And so it might not be those same 4 Lego pieces that you put together, because she's broken them apart, you've put them back together. She's broken them apart, you've put them back together. So they call that macroscopically not changing. From the big picture, it doesn't look like anything's changing, but microscopically, things are changing. So it's a dynamic equilibrium. There's a good video that I can point out to you on Schoology that shows just an everyday example of a guy throwing a ball over the wall, or actually I think it's apples, but I'll point that out and maybe rename that on Schoology so you guys can see that. All right. What else should we go through? All right, I think by this time you've probably gotten the idea that you have to do these equations that are called equilibrium constants. So we have this equilibrium constant equation, and you always take the concentrations. Remember, that's what the square brackets mean, is concentrations. And you take those concentrations of each substance, and then it gets raised to a coefficient. And that coefficient is to raised to a subscript, and the subscript is whatever the coefficient is for that problem. So if this right here was a 1, then the concentration is raised to the first power. So you've got that. If this right here, this B, was a 2, then the concentration of B would be squared. If this was a 3, the concentration of 3 would be cubed, and so forth and so on. And then you always want to remember that the KEQ is always products over reactants. And so if we were in class, every single day I write that on the board 2 or 3 times a day, products over reactants, products over reactants. Okay. And then again, remembering that the concentration is those square brackets, and that is always the molarity. Remember, molarity is moles per liter. And so we did that in the last unit. Another thing to remember is that concentrations are only going to be used if they're in the gas state or in the aqueous state. So when you see gases, or if you see aqueous, you're going to use those. Solids and liquids get ignored in the equilibrium constant, so you do not include them. The next thing that I wanted to quickly talk about is if you have a KEQ or an equilibrium value. Remember that KEQ is products over reactants. Okay. If you have a KEQ that's greater than 1, we'll start with this one. They say that the products are favored. I just make up numbers, and this is how you can kind of think about it. If you had products being favored, you would have more products. So for example, we'll say that we have a concentration of 2 for our products, and 2 over 1 would give us a KEQ of 2. So that would be a number greater than 1. So we have this concentration, this equilibrium constant that's greater than 1, and that means that you have more products right there. If reactants are favored, you're going to get a number that's less than 1. So for example, if you were to plug in numbers and you put in something like this, you would get an answer that's less than 1. So you have a KEQ, an equilibrium constant that is less than 1, and you can see that you have more reactants. You had 2 for your reactant, which has more. So they say their reactants are favored. Okay. All right, pause for just a second to see what we want to go through next. Oh, the last thing that real quickly is that it's temperature dependent, meaning that the temperature can change your concentrations, and so your KEQ can change. We're not going to worry about that right now. We're not going to do anything with different temperatures, but I just wanted to point that out. All right, something to notice in this example is you do have liquid and a liquid. Again, remember those are going to get ignored, so you would not include those in your equilibrium constant. So you'd have something pretty simple for this one. You'd have products, which is going to be our oxygen. So we have the concentration of oxygen. There is no coefficient, so we can just leave that alone. Actually, this is not a balanced equation, but I don't think that's going to matter because we're going to do 2 here. We got 4 and 2 there, so it doesn't affect it anyway, but we'd have this, and then we would have nothing in the rest of the products and nothing in the reactants. It would be super simple. Same thing with this one. The solids are going to get ignored, so you're only going to include the gases, and if there was aqueous. Okay, we skipped reaction quotient for now. We're going to come back to that. All right, these were just simple finding either the KEQ or finding the missing concentration. If you have any questions about that, make sure you email me, but that usually is fairly straightforward for people. All right, then we started with ice tables, and Mr. Park talked about ice tables. So ice tables are going to be super helpful in solving most of these. Sometimes you'll make an ice table, and then halfway through you realize you don't need it. But your go-to is going to be to start with an ice table. Start with an ice table every time. And you may end up needing it. You may end up not needing it. But that's going to be the general idea. So I'm just going to go through this example. I know you might have already done it, but in case you don't remember it, I like to rewrite the equation. And as I rewrite the equation, I kind of pay attention to the states of matter. I'm going to include gases, so that can be included. And if it was a solid or liquid, I would just put a big X through it. I would cross it off. But these are both gases, so I'm going to leave them alone. I'm going to make my ice table over to the side. I don't usually put the boxes in for the data table, but you're welcome to. I'm going to go ahead and read through it. We've got 0.30 moles of N2O4. Moles is not helpful. You're going to want to use it. Your brain's going to want to automatically put it in, but we need molarity. These ice tables use molarity. So I'm going to use this 0.3 moles and the 2 liters. And sometimes I'll put a little kind of arrow over and show that I'm going to do a little pre-work ahead of time, where I'm going to convert this to molarity. So I've got moles over liters, and that will give me a molarity of 0.15, and that I can use in my ice table. So it's N2O4. It says that 0.3 moles is placed into 2 liters. What will be the equilibrium concentration? So I'm going to assume that they're placing this in there initially. So I'm going to put in my 0.15 as my initial concentration of N2O4. It doesn't say anything about the other gas, so I'm going to assume that there's none of that at the beginning. it asks for the equilibrium concentration, and that would be kind of what goes into this area and this area. Okay. It doesn't give me any more information besides the KEQ. But remember, the KEQ does not go in our ICE table. Only concentrations, only molarities. Concentrations, remember, are our square brackets. So I don't have any more information. So I'm going to have to assume that the concentrations are changing. I just don't know how much. So this concentration of 0.15, let me just start right here again. This 0.15 is going to change. This concentration of 0 is going to change. The only thing that can happen is the 0 is going to be able to gain into, we're going to be able to add a concentration. The reaction must be moving in this forward direction because we didn't have any of it, any products to start. So it's the only thing we can do. We could only go in that forward direction to start. And then if this is gaining, then our reactants must be losing some amount. Again, we don't know how much, so we're just going to say that the reactants are going down by some amount that we'll call X. And so we're going to use that variable X. Now, at the same time, my products, my NO2 over here, are getting an increase in concentration. The reaction is moving to the right in the forward direction. And so they're going to be increasing by some amount, which we're going to call X. But since there's a 2 here, those coefficients are going to play a big role. We have to include that because that mole ratio is going to affect the concentrations as well. So my final concentration at equilibrium is going to be 2X. We don't know what that value is yet, but we're going to calculate that. And then over here, it's going to be 0.15 minus X. Something I like to do is I like to add a 4th line onto my ICE tables. If you like to make them into data tables, you can. Okay. And I add that 4th line in because a lot of people forget to actually answer the question. The question is asking what will be the equilibrium concentration of the gases. This answer that I have in the box, this 0.15 minus X and this 2X, those aren't my final answers. I can't use X as my answer. So I'm going to go ahead and use my I'm going to have to use my solver. So the first thing I do is I like to just write it out. So over here we have KEQ, and we're going to have products over reactants. So my products are NO2, and I'm going to square it. And the reason I'm squaring it is because of the 2 that is in front of it as a coefficient. Okay, there's no other products, so I'm going to leave that alone. My reactants are going to be my concentration of N2O4. There's nothing in that spot because there's just a 1 here, and so we just leave that alone. Okay, now I'm going to start to fill everything in. My KEQ was given up at the top as 4.50. My NO2 is now going to be that 2X that I had over here, and don't forget that you have to square it. It sort of gets double used is what I always say. So yes, I have the 2X, but I also have to include this 2 coefficient as my superscript. On the bottom, I have my concentration, which is going to be 0.15 minus X. Okay. There is nothing except for the 1, so you don't have to put anything in there. All right, as soon as I see X's, I'm going to have to use my solver. Okay, this is where it gets a little tricky. I'm going to try to make a separate video on with my calculator showing that, but I like to kind of write it out. Now, my calculator is an 84. I don't have the 2 boxes that Mr. Park talked about, and I'm just going to scroll back real quick so you can see the directions. If you just follow them exactly, maybe I'm missing it. Oh, hold on. Let me go the other way. Oh, there we go. It was right next. If you follow them exactly, you should be fine. Now, I don't have the 2 boxes, so I'm going to be doing the entire equation, which is going to be set equal to 0. So I'm going to show you how I'm going to do that right here. So let me take this equation, and I'm going to show you how I would type it into my solver. So because it has to be set equal to 0, I'm going to subtract away the 4.50 on both sides. Okay, and so how I'm going to type it in is I'm going to have my parentheses at the top. I put the entire thing in parentheses, and then I add another parentheses for the top. Okay, and so it almost gets double parenthesized. So I'm going to have my 2X, which is going to be squared, Because it's divided by, I'm going to add my divided by. Now in the bottom, I'm going to parenthesize that as well. 0.15 minus x, okay? Nothing's happening with that in terms of coefficients or superscripts. I'm just going to leave that alone. And because I opened my parentheses here, I'm going to close those double parentheses there. Okay. And then last but not least, this is the part that I sometimes still forget. I'm much better at it now, but I've done a lot of example problems, so you're probably going to forget that sometimes, is to make sure you set it equal to 0 by subtracting away that 4.50. So don't forget to put that in. Okay. And then you're going to type this into your solver, and it should look exactly like this. Okay. If you have the 83 or the 84. If you have the two boxes, you don't have to do this part. Okay, you would just set that on the next box, which is even easier. All right, once you type it in, you're gonna hit enter, but then you have to still do your 0 alpha enter, which is sometimes the second thing that I sometimes forget to do. So after you type it all in, we've typed everything in. Okay, we're gonna hit enter. It's gonna give you an answer. You're gonna think you're done, but make sure you hit 0, the alpha button, and then the enter button. So what I would do if I were you is I would pause this and I would try to type it in. I'm going to type it in at the same time, so hopefully we'll end up to be right around the same time. So I'm going to my math button, which is in the top left. I'm going to go down to solver. I've used mine, so I'm going to up arrow and clear it. Okay, now it just says 0 equals. I'm going to put in both parentheses. I'm opening them, and then I'm going to open my top line. 2x. I'm going to close the first set of parentheses and then use my squared button. Divided by. I'm going to do my next parenthesis, okay, for my bottom denominator. And I've got 0.15 minus x. I'm going to close that first, that denominator parentheses, and now I'm going to close the entire thing with another set of parentheses. So I start with a double parentheses and I end with a double parentheses. And don't forget minus 4.50. I'm going to hit enter. It's going to give me an answer, but I have to now hit 0 alpha enter. And then I'm getting my x value as 0.13. I tend to make a lot of mistakes typing this in, and so do my students. So I always type it in twice. And if I get the same answer twice, I feel pretty good about it. If I get a different answer twice, I try again. If you get an error, it's probably something that you typed in wrong, a parentheses. Okay, so follow those instructions very carefully. Now you're not done. That's why I add that fourth line in to the ICE table. I'm going to take that 0.13 and now plug it in and plug it in for my final answers. So you can quit out of your solver and then just type it in. And I'm going to get 0.26 for my final concentration of NO2, my product. And then 0.02 for my final concentration. Remember, these are concentrations, so they're going to be in molarity. Phew. Okay, so I'm going to stop there for today. Tomorrow I'm going to add another one which talks about Q, which is very similar to KEQ, and then you're just going to be doing something with the answer, but you'll notice that it looks very similar. So hopefully this helped. Please email if you have any questions. I can make another video and post it as well.